Hi and good afternoon. The title of the presentation is titled Knickpoint Mapping in the Middle Shire Basin, the Malawi Rift, and its implications for the evolution of rift interaction zones. My name is Zuze Dulanya, and I'll be making this presentation on behalf of the collaborators that you can see on the screen. As a way of introduction, early stage rifts are important places for the understanding of the development of continental rifts as they set up the location of continental breakup margins. Traditionally, in well-developed reefs, seismics and other related techniques have been used to understand their evolution. In incipient reefs, we have low sediment volumes, and this inhibits detailed environmental reconstructions. However, these incipient reefs are areas where we have active deformation and faulting, which produces geomorphic indicators that could be useful to investigate scene rift landscape evolution. Part of our study area, the Zomba escarpment, is shown in the photo above, and you can see the Zomba fort in the foreground. We can also see the topographic profile of the same area, showing some major structural features including the Zomba fort, the one that I just showed you in the photo above, and other related faults that control the Zomba graben, together with the thin sedimentary cover that is present in the area. We can also see an example of one of the geomorphic indicators that are present in the area, the Kapikira Falls, in the lower right photo. Our study area is part of the western branch of the East African Rift System at the southern end, and this is called the Malawi Rift. Tectonic maps of the Malawi Rift are shown and represented differently by various authors, as you can see in this image. Our interest is in the area which has the black square at the bottom in both of the maps. What is interesting to see is that both maps emphasize different structural features in the study area. For example, the map by Njinju and others show that this area has two main boundary faults compared to the other one, which emphasizes one main boundary fault in the study area. The bottom map tries to show our area in relation to the main tectonic features, of course also trying to integrate the various interpretations by Jinju and Fraser et al. To include other structural features that are not shown. What is interesting to see here is that the main Zomba fort connects the Upper Shire Basin to the Lower Shire Basin through the Middle Shire, the area that is shown in the red square, which is our study area. In terms of the geology, the Middle Shire area is here, and then we have the Upper Shire here and the Lower Shire. The area in the Middle Shire is dominated by the Proterozoic metamorphic rocks which have been metamorphosed to amphibolite and granulite facies metamorphism. The Upper Shire, on the other hand, is dominated by superficial cover of Cenozoic age belonging to the East African Rift System. In the Lower Shire, we have the Cenozoic rift sediments, but also the Permo-Triassic sediments belonging to of Karoo age, which are shown as sky blue, and then Cretaceous sediments, which are shown as yellow color. This emphasizes that the Lower Shire is an area of active extension for a long time from the Permo-Triassic to the present, unlike the Upper Shire, which has been opened by the East African Rift System. The Lower Shire Basin, just to emphasize what I said earlier on, has been an area of active extension at various geological times, and we can see the northwest-southeast extension that was predominant in the region from the Karoo Age, and then it rotated to the northeast-southwest extension in the Cretaceous times, resulting in various dike injection and deposition of various sedimentary units in the lower Shire Basin. So this is our study area. We see the Cenozoic rift sediments shown in dark gray here in the upper Shire Basin and the same in the lower Shire Basin, together with the main tectonic structures that control the upper Shire, the lower Shire, through the middle Shire section. The middle Shire area, the study area that we're talking about, is shown in the red square here and has been described as a breached rift interaction zone recently, by the way, by Kolaole and others. And these interaction zones are areas where we have two different segments of the rift trying to integrate or coalesce to form a transfer zone. But before their coalescence, they develop into a rift interaction zone. Based on the work by Kolaole and others, we can see different geometrical representations of the interaction zones. Our study area is described by this work as an oblique overlapping zone represented by these geometries. And what we see in this map is that we have part of the Malawi rift trending in the north-south direction and in the north in the upper Shire, for example, and then the Shire Valley has a major trend of northwest-southeast, and the middle Shire is found in between these two zones. So the middle Shire tries to bridge to merge the two segments of the rift through this oblique interaction zone. The middle Shire area is part of the lower Zambezi Basin. So the Zambezi River is a major river that flows through Zambia, Zimbabwe, Malawi, and eventually Mozambique before it flows into the Indian Ocean. And if you take a longitudinal profile of the middle Shire section, you see that it has a step-like topography, and the lower Shire is on this end, the upper Shire is on the other end. The lower Shire is at less than 100-meter altitude above the sea level, and the upper Shire is above 500 meters above the sea level altitude. This is the same topographic profile that I showed you earlier on, showing the major structure features and the middle Shire segment with thin sedimentary cover, together with other major structure features in the study area. The key science questions that this study tries to answer are the following. The first one is, how does the scene rift landscape and depositional environment evolve in areas where we have rift interactions and linkages? The second question relates to the roles of the pre-rift and sim-rift structures in the landscape evolution and how these evolve in the rift interaction zones. This study made use of the power law relationship, which expresses the slope channel as a function of the steepness index and the drainage area raised to the power negative theta, which is the concavity index. The parameters in this equation are dependent on the basin morphology, the underlying rock strengths, and the hydraulic geometry, and they can therefore be used to indirectly evaluate the river system responses in relation to the landscape forming and modifying processes, such as the tectonism and deformation that are present in the area. So for this work, we used a digital elevation model from SRTM with 30-meter resolution for river profile extraction and identifying breaks in the river profile, which we described as Knickpoints, using the Topo toolbox in MATLAB. We also used MATLAB to produce chi plots, which we use to describe the states of drainage divides. That is, to describe whether the drainage divides are in static or disequilibrium or in equilibrium. And also use the same chi maps to estimate the rates of migration and therefore make a tentative estimate at the edge of the evolution of the Middle Shire Basin. The results that we have produced, we produced based on this analysis, show that the river profile is controlled by various factors, including tectonic features such as the major faults, like the Cholo fault that you can see, but also some lithological contacts, for example, the contact between the amphibolite and granulite fascias and other rock units that are present in the area. We also see that there are various types of Knickpoints that are present in the area. For example, vertical step Knickpoints versus slope break Knickpoints, as you can see from this interpretation. We also see that the Knickpoints, the green dots that are shown on this plot, are clustered according to some structural features. For example, the major boundary faults that we see in the area, but we also have some Knickpoints that cannot be precisely described or ascribed to the major tectonic features in the area. So there's some clustering that we see in the area related to structures and other factors in the area. Based on the chi plots, we see that we have drainage divide migration in various parts of the study area. So the red arrows indicate the direction of migration of the drainage divide, depending on whether you have high chi values on one side versus low chi values on the other side. So we see that the drainage divides are migrating generally in the direction where we have these major boundary faults. If we plot a chi plot for the axial rivers, the Shire River, the main river in the study area, we also see that the high chi values are in this northeastern end compared to the low. If you can compare these values on the scale that is provided, and this can be used to infer that the direction of drainage migration for the main axial river is towards the southwest, where we have the major faults, for example, the Lisungi and the Cholo fault. We have used the same chi values to estimate the rates of drainage, the Knickpoint migration, but also a control to produce a control plot which we can use to estimate the edges of opening of the middle Shire to the upper Shire and the connection with the lower Shire Basin. And based on this interpolation, we see that the middle Shire section might have opened within the time interval of at least the mid to upper Pleistocene compared to the rift shoulders which were of slightly older age of greater than middle Pleistocene to lower Pleistocene. The rates of Knickpoint migration are also variable depending on where you are in the rift. So within the boundary fault area, we see that the rates of migration are slightly lower at 0.06 meters per annum compared to the middle part of the middle Shire, the actual river system, where the rates can go up to about 1.3 meter per year. That is, we have faster rates in the axial region compared to the boundary fault regions. In terms of the age and evolution history of the area, we therefore see that the Middle Shire section was opened into the Upper Shire at least during the mid to the Upper Pleistocene times, whereas the Knickpoints started to form at least during the Lower Pleistocene times. And so the connection between the Upper Shire segment to the Lower Shire segment through the Middle Shire might have taken place during the mid to the Upper Pleistocene times. But we also see that the opening was preceded by an initial uplift, perhaps triggered by the southward propagation of the major boundary forts, for example, the Zomba Fort, the Lisungu Fort, and the Wakumas Fort among the many forts present in the area. In conclusion, therefore, we observe that the Middle Shire might have opened during the mid to the Upper Pleistocene times, and that its development postdates the development of the Lower Shire segment and the Upper Shire segment. So it's younger than the two segments of the Shire, but also that the Middle Shire section does show a strong unequilibrated longitudinal profile along inherited basement structures, which seem to modulate the Knickpoint locations. And that finally, that the observations that we make in this study support the hypothesis that the rift system, especially the western branch, has developed from the gradual propagation, linkages, and coalescence of initially nucleated distinct rift basins. Thank you for your attention. This marks the end of the presentation.
Okay, thanks a lot, Zuze. There are already some questions in the chat. Alex, you are first.
Yeah, cool. I really enjoyed this talk. It's an amazing area. You talked about just at the end the coalescence of fault segments, and I wondered whether or not the multiple Knickpoints that you show on individual channels, do they reflect multiple changes in base level as these channels have responded to the active faults?
Yes, they relate to multiple changes in the base levels, because we think the main boundary fault, the Cholo fault, is readjusting over time. Remember from the presentation, I did mention that it's part of what initially was the Karoo Basin, but it has been rejuvenated over the course of geological time. So as it does this, I think there are base level changes that force the upper streams to readjust to the lower, to the Cholo fault.
Okay.
Sure.
Okay. Becky, you had a question as well, or is it already answered?
Well, I guess I was just wondering if there could be some control of variable bedrock lithology and some of those multiple Knickpoints. Have you thought about that?
Yes, there are some lithological controls. On one of the slides, I did show some of the Knickpoints and how they are responding to bedrock characteristics. So I did, for example, show how some of the Knickpoints plot on the contacts between the amphibolite and granulite fascias,
Yeah,
and of course other rock types in the unit. But
Yeah.
we think these are fewer compared to those that are readjusting due to tectonic controls. So if you looked at the plot on of the various Knickpoints, you see that quite a good number of those are along the main structural features and not on the lithological controls.
yeah, that's really interesting. Thank you.
Thank you.
I think